AG is of general type for G greater than or equal to 7, and it's unirational at least. Yes, I think I do mean unirational at least for G less than or equal to 5. And just by the way, for G equals 6, what we know is that the dimension 8 over A6 is not negative. Not anything more about that. So this is all happening over the complex numbers, and so there are obvious questions. And the most obvious question, perhaps, is, well, what happens over, say, the rationals? And so over Q, well, I mean, general type is general type. We're kind of stuck with it. Of course, positive characteristic, there could be more questions. But over Q, I'm really interested in these small numbers. And so A1 is just the J line, there's nothing to do. A2 is, I mean, there's explicit equations written down by Iguza, and there's nothing to do, really. And those are rational. And so what about, so the remaining cases then are G equals 3, 4, 5. I will explain how we got interested in this when I get to the point where we answer the question that we were asked. But these are reasonable questions in themselves. And another thing is that, in fact, A3 is actually rational. Over C, sorry. So you could also, so I could ask about unirationality over Q for G equals 4 and 5. And for G equals 3, I'd like to know unirationality, but there's potentially one could ask for finer results than that, at least some hope. We don't know anything about whether maybe the A4 and A5 are possibly rational for over C. We don't have any further information about that. Okay. So those are the questions, and I'm just go through some of these and say what we found. So the first theorem is that, and so this is that A5 is unirational over Q. So what you do, this is actually not very hard, really. What you do is you go and look up all the proofs that A5 is unirational over the complex numbers, and you go through them until you find one that you like, and where you can see what's going on sufficiently clearly to be able to check whether it works over the rational numbers. And so there are several of these proofs. I won't list all of them, but this one is really just a matter of, this is very similar, well, essentially identical to the proof, which is one of several. And this one is due to question Vera. And it's and what you do is you take you fix I think it's you fix 4 points in P2, and call them U1 up to U4, and you look at hypersurfaces of pi degree to 2 in P2 cross P2. And I want them to have, I think I want them to have double points at the 4 points UI, UI. And then you look at the projection of those onto one of these factors, doesn't matter which one, of course, as everything we've written is symmetric, and that gives you a conic bundle with a discriminant locus, and the discriminant locus is a sextic curve with nodes at these 4 points, and that has the right genus. After normalization, it has the right genus. So the discriminant locus gives you, as we saw in the last talk, gives you a double cover of a curve of genus 5. And then you have to check that that gives you, you get almost every prim that way. And you get almost every prim, and then the, so this gives by discriminant. So project. Two, and this gives via discriminant a map to R6. I mean, if I vary these, if I look at the family of these hypersurfaces, and R6 comes with a map to A5, which just forgets the, which is the well, I mean, the prim variety is of, you know, the cover has genus 11, so the prim has is a principally polarized abelian variety of dimension 5, and the point is that this is generically surjective. So there are several other proofs of this unirationality of A5, but they all seem to go via the prim by some means or other. I don't know any proof of unirationality of A5 that does not also prove unirationality of R6. Anyway, so this argument basically straightforwardly works over the rationals. We didn't really have to do any work at that point. Some of the others probably also work over the rationals. It's a little bit, it's just a little bit more difficult to check that they really help, that they really do, or they really do the way that they've been written. So that's case of G equals 5. G equals 4 is rather similar. And so the same statement, A4 is unirational. And then over Q, same general idea. It's very slightly more complicated, but this time there are lots of different proofs over the complex numbers. They don't all go via prims. Some of them go via the universal family over this A4, and some of them go via intermediate Jacobian cubic threefold. And these are, and that's sort of less. I mean, we can now do that. We could, in principle, do that with over non-closed fields, but it's much less clear. I mean, the intermediate Jacobian is historically it's an analytic construction. You produce a complex torus, and then you somehow produce an ample line bundle on it analytically, and then you say, oh, it's an abelian variety all along in this particular case. So the proofs are written in that analytic way, so you'd have to go back and check that everything's could be, you know, see how to make the reg all the way through, and then see whether after you've done that it still worked over the rationals. Probably does, but there is a and this is, I suppose, why I'm the person who got asked about this. We use a proof that goes via R5, R5, and this is due to Alamizadi, Marco Lo Giudice, and me, and this is from about mid-2000s sometime. So Marco was my research student, and what I was trying to do was to find out why R5 was unirational, with the idea of using the construction to do something, and I couldn't find out why R5 was unirational, because it eventually turned out that actually, although everybody assumed it was, because the unirationality of R6 was known, nobody had ever actually bothered to check the unirationality of R5, so we did. So the proof is similar in spirit to this one. I won't give the details because I've no time, but you construct a conic bundle with the right properties. The construction is somewhat more complicated, and there's a little bit more care needed to check that everything works over the rationals. The point really being you get this covering space. It's not immediately obvious. It's rational, but it's not hard. But basically, this works in the same way. Okay, so we have these two results, and before I move on to G equals 3, I will give a corollary, and the corollary is really where this all started. And so corollary is due to these very well-known people, and what it says is that there are things even over the find the exact statement. So there exists a Hodge generic principally polarized abelian G-fold over Q, which is for G equals to 4 or 5, is not isogenous to any Jacobian. So what happened was they wrote this in a paper of theirs as a conditional statement. This is a special case of a stronger statement, and it's not to any Jacobian is not particularly the point. I mean, there are many other classes of abelian varieties for which this would be true, but the point is that you have these abelian varieties that live on some subvariety in the moduli space, and they're allowed to move around with isogenies. How many of the rational points do you hit when you do that? And the answer is not all of them, but in this case, but this is conditional on the unirationality of these moduli spaces. So the starting point of this was an email from them to me saying, do you know whether this is unirational over Q? And I didn't. And then they told me why they wanted to know. And this seemed like a good reason to try. So all this.
Sorry,
yes?
What is meant by Hodge generic?
Hodge generic. Well, I mean, it means the Mumford take groups are what you would expect, GSP, but really what it means is it's not lying in any special subvariety, anything that's defined by some modular conditions. That's just okay, so this is, I mean, this is a nice consequence of these fairly straightforward verifications that we do. What about, I'm all right for time. So what about G equals 3? G equals 3 is, well, unirationality is not so hard, but the thing is we know more we know that A3, the coarse moduli space A3, is rational over the complex numbers. And the proof of this is by Kliatchko. It's very complicated. There is a paper by Böning which attempts to organize and explain Kliatchko's proof. It's still very complicated. It's a lot of invariant theory. And what it's actually doing is it's not working with A3 at all, it's working with M3. And the problem with that, as far as we're concerned, is that, well, there are two things. One is going through that and trying to find out whether it works over the rationals is going to be very hard. We did try. And we decided it was going to be very hard. And the other thing is that that's giving us something for the coarse moduli spaces. But but the coarse moduli spaces now are not the stacks are not the same. M3 and A3 are birational, essentially the same thing as coarse moduli spaces, but the stacks are different because an abelian threefold has an automorphism, a G of 3 curve does not. So G equals 3, A3, but it's M3 really, is rational over C. And this is too hard over Q. By too hard, I mean, you could try. There are quite a lot of proofs, rationality proofs in theory of curves, which go by some sort of more or less classical invariant theory. And in principle, you could pick up one of them and try to see if it works over the rationals. Nick Shepherd-Barron is not here anymore, but he's one of them. There's one that he wrote, which was actually done because he's Nick Shepherd-Barron. He did it carefully over arbitrary fields, but mostly people who've written these things have just worked over the complex numbers and not worried too much about fields definition. So you have to go right back through the proof. Well, if you're going to do that, I mean, it's an exercise. You could do that, but you probably shouldn't start with this one because this is the most complicated of all those arguments, pretty much. So, you could work up to that, but this isn't a good one to start with. Anyway, we have an application in mind, and for the application, we don't need rationality. So our theorem is that over Q, 3, and which is M3. So for the moment, I'm still thinking coarse moduli spaces, is stably rational. How much do I want to say about that? I think probably not as much as I would like to say about it, given the time constraints. So we're still using a bit of invariant theory, but you don't have to use nearly so much. So just what do I want to say? Well, and so what you do is you look at it's actually we prove something more. We prove, so this is these are hypersurfaces of degree. So more generally, you look at H0 of OPN of D, and you look at the action of SL n plus 1 on that, and this quotient is close to being, but the SL, not PSL here, is close to being the coarse moduli space, the parameter space for hypersurfaces of degree D in Pn, some conditions on D and N here. So what we can do is we can prove we can stable rationality for most values of n and d and the quotient plus a bit. I mean, there's the mu. What are the roots of unity that give you the drop you down from SLN to PSLN is stably rational. And the thing is that what's rational is this quotient cross SLN. So the quotient, let me call this W, W cross SLN plus 1. That's the thing that's rational. And so the point here is that SLN plus 1 is rational. And so when we wrote the paper, we had an argument which said that it works for large class of reductive groups by some sort of decomposition. And it's pointed out to us by the referee, this is totally trivial because you just look at the determinant, it's linear in any of the coordinates. So you just just drop one of the coordinates and that gives you a map to AN. Yeah, totally obvious thing. So yeah, after you've been thinking about stacks for a while, you start to you kind of stop thinking about things like that, and then basically. Okay, so I've got 5 minutes, right? So what do I want to say? So I want to tell you some consequences. And so one consequence is about lifting abelian threefolds from characteristic P to characteristic 0. So the statement that we have is do I want to say it this way? Right. So what I'll do is I'll fix AP is a principally polarized abelian variety over FP. So this is just some prime P. You can have P run over some finite set of primes if you like, but one will do. Principally threefold. This is strictly for dimension 3. So if AP is a principally polarized abelian variety of dimension 3 over FP, then there exists, have I got this the right way around? Yes, I have. There exists A, which is a principally polarized abelian variety over Q, such that the reduction of A mod P, so A FP. So by this, I mean that you take the Néron model, you take the reduction of that mod P. And this is AP. So I've lifted AP through characteristic 0. Now, there's no chance of doing this for large dimension because the rational points should live in some small subvariety. If you believe the Bombieri-Lang conjecture, then if G is large, the moduli spaces of general type, so the rational points should live in the rational points over Q should live in some subvariety somewhere, the points really in characteristic P, of course, are all over the place. So there's no chance of this working in general, but stable rationality is enough for this. Getting this is actually quite delicate, and this is because of Galois twists. The point is you can lift as far as QP without too many problems. but then when you try to lift all the way up to Q, you don't immediately know that you're not going to end up with some twist of the thing that you so you want to, if we have a proposed lift to Q, it might be doing the wrong thing. And what you have to do, this is where you have to be careful with stacks. I mean, what we have to do is we prove the stable rationality for the coarse moduli space. And that implies weak approximation for the coarse moduli space. And what we need is, what we need is weak approximation for stack. And so I'll just really write back. I'm not going to have time to eat. Maybe I'm not going to be quite as stacky as I thought I was going to be, because I'm going to run out of time. So we need weak approximation for, and now we need it for stack. The thing about this is that, yeah, that's all right. And the reason it's all right is that this has this has the map to A3, and this is a mu2 gerb. Gerb is stack for principal bundle. And what we know is there is a theorem of Shimura which says that this is, in fact, that for this case, that this is what is called a neutral gerb, that's stack for trivial bundle. Of course, Shimura didn't say it like that. But this is this thing about the difference between field of definition and field of moduli. And he produces a model of generic abelian G-fold over the field of definition. The thing here is that this works because so this is a mu2 gerb. It's trivial, so a section, and you can be consistently on whichever whichever twist you want. But this works because, and this is, as I say, it's a theorem of Shimura, G is odd. This is the condition in Shimura space, completely false. It's actually false for G even. So what that means is if we could prove if we could prove stable rationality for A4 and A5, we would have this result for A5, but not for A4. For A2, it's all right for a different reason, because you can just write down a hyperelliptic curve, and you just write down the equations, you lift the coordinates. Lift the coefficients, there's no problem. So there's this peculiar thing that it all works nicely for odd G. Well, I mean 3 and 5, it certainly isn't going to work beyond that for the same reason. Okay, I will stop there. There is another corollary about weak approximation, but I think that's enough to be getting on.